Thank you, Mr. Chairman, for the introduction. Alright, my talk will be about crack propagation under whole-time conditions in a nickel-based superalloy, which is called Inconel 718. To introduce my topic, I would say that in air engines, we have critical components like high pressure to bind this, which have to meet the certification requirements regarding the fatigue crack propagation life. And by fatigue, I mean pure sinusoidal loading cycle. However, as you can see, illustrated here, the real in-service loading condition is quite more complex, and therefore we decided to investigate the effect of whole-time cycles, like this one, which are, I would say, more representative of the real in-service loading conditions. Assuming such loading cycles, we have to take into account different contributions to the crack growth, which are the fatigue contribution due to the loading and unloading part of the cycle, the creep contribution due to the whole time at maximum load, and finally the effect of environment, since all our tests have been performed at high temperature, and ultimately all the interaction between those contributions. Alright, let's have a word about our experimental procedure. We performed crack propagation tests using single-edge notch specimen. We have a straight through thickness starter notch machined by electro-discharge machining on the right. And we monitor the crack lengths using the direct current potential block data, the well-known DCPD technique. We investigated different cycles, one which is our reference cycle, a pure fatigue loading cycle at 2 Hz of frequency, and triangular 10 cycles with 10 second loading, 10 second unloading, and finally whole-time cycles with 10 second loading, 10 second unloading, and different whole-time of 5 minutes, 20 minutes, or whatever. And all of those at 550 degrees. Without further ado, let's have a look at the results. Here we have our reference cycle, a 2 Hz frequency sinusoidal cycle. You can see that comparing it to the 10-10 cycle, there is a tremendous effect of loading frequency. The loading frequency is decreasing and crack growth rates are increasing. And you can see that crack growth rates are also increasing with the application of a whole time at maximum load. About the crack growth mechanism, we observed typical transgranular fracture surfaces under 2 Hz fatigue cycle. And for all the other cycles from 10-10 and all the different whole-time cycles, we obtained an intergranular fracture. Okay. In order to investigate the fatigue and the creep contribution, we decided to acquire continuously the DCPD signal in order to extract the crack lengths occurring at load reversal. So this is the fatigue contribution. And the crack increment occurring during the whole time itself, and this is the creep contribution. So with this, we are able to get 3 DAD and delta K curves from one test. You have the blue one, which is the classical DAD and delta K curve considering the whole cycle. We have the red one, which corresponds to the fatigue contribution only, and it represents, let's say, 90% of the crack propagation. And finally, the green one, which was extracted from the whole time itself. In order to investigate the damaging effect of whole-time cycles, we have performed tests that were presented in the literature consisting in alternating crack propagation under whole-time conditions, then applying a pure fatigue cycle, and then back to the whole-time cycles. What we can see is that at the beginning of the application of the loading, sinusoidal loading cycle, there is transient and with decreasing crack growth rates, and we are able to measure the crack growth extension. Depending on the source, this is believed to be the sign of a damaging effect of the environment that has occurred during the first step, and even it can be related to the size of the so-called damage zone at the crack tip. Moreover, if we have a closer look at the fracture surface, we can see that under whole-time condition we have a large degree of crack front curvature, and it appears quite rough, I would say. While when we apply pure fatigue cycles, you can see that the crack curvature unfolds, and we once again get, I would say, almost straight through thickness crack. And from this observation, we decided to investigate the effect of crack front shape on the crack growth rates measurement. The results I have presented you previously were analyzed assuming a straight through thickness crack for the DCPD for the crack length measurement and delta K calculations. As you can see, if we apply a 2 Hz cycle or a 10-10 cycle, this is a good assumption. But if we apply a whole time cycle, the hypothesis of a straight through thickness crack is not valid. So we will investigate this effect numerically. The procedure we decided to use consisting replicating the exact crack front shapes from fracture surfaces under whole time conditions. This is the previous test. We will insert it into finite element mesh and perform crack growth simulation with a simple Paris law. And during the numerical crack propagation, we will simulate the direct current potential drop technique. And ultimately, we will analyze the DCPD, the numerical DCPD value with the exact same assumption as per experiment, assuming a straight through thickness crack. So you can see that if we make curve crack propagating, at the beginning of the propagation, the curvature will quickly unfold, and afterwards, the crack front is almost straight and propagates mostly by translation. By applying the DCPD method, in order to get the DAD and delta K curve, we get, once again, this kind of junction, and it is found to be in very good agreement with the experiment, the corresponding experiment. And from this, we are able to say that this tangent corresponds to a geometrical effect on the DCPD method, since at the beginning we have a curved crack front, and at the shoulder of the tangent we have an almost straight through thickness crack. So this is believed to be the sign of unfolding crack. So there is an effect of crack curvature on the DCPD method and the crack growth rate measurements. Well, let's go one scale further, I would say. We decided to investigate the effect of crack tortuosity, since you can see the crack front is all but even. So we decided to represent a tortuous crack front with a sinusoidal crack front infinite element mesh. Once again, we simulate the crack propagation and apply the DCPD data. But first, let's have a look at the delta K distribution along such a crack. You can see that in the depth of tortuosity, you get some very high delta K value, while at the top of tortuosity, the delta K value is almost 0. And we can compare it with the assumption of a straight through thickness crack of average coefficients of 2 millimeters. So assuming, once again, a simple Paris law and linear elastic fracture mechanics, we see that the crack tortuosity will unfold. Now we apply the DCPD method during the crack growth algorithm. With the dashed line, you have the Paris law, which was used to drive locally the crack growth rate. And the different points you see correspond to the crack growth rates that was measured using the DCPD technique during the numerical crack propagation. And you can see that the tortuosity tends to increase the measured crack growth rates. If we compare this to some experimental results, here we have, let's say, 10-10 cycled experiment. This fits the Paris law used in simulation. If we now compare this to the 5 minutes all-time cycles, we have an increase in the crack growth rate, and you can see that it matches pretty well with, let's say, 40 or 80 micrometers tortuosity amplitude. And if we compare this with 20 minutes all-time cycles, the crack growth rate fits pretty well with 200 micrometers tortuosity. So we are able to match experiments and simulation. Finally, we will assume that crack growth rates under whole-time conditions are strongly depending on the crack front shapes. To start with, we will consider that we have an initial state with a straight through thickness crack, a very even crack front. And during the creep, we believe that tortuosity will initiate due to local interaction between microstructure, mechanical fields, and maybe environmental effects. And during the load reversal, the fatigue contribution to crack growth, this tortuosity tends to unfold, assuming linear elastic fracture mechanics is still valid in such a case. And so the crack growth mechanism is believed to be a progressive build-up and destruction of crack tortuosity. So we still have to understand why does a crack curve itself and why it is so tortuous under all-time conditions. And we will investigate the effect of microstructure by performing different thermal treatment. And we will also see if it is related to environmental effects. We will check this by performing progress tests under vacuum. Thank you.